Okay, so picture this. A power source with 0 moving parts that's incredibly efficient, can run on all sorts of different fuels, and it operates at temperatures hotter than lava. Sounds like something out of a sci-fi movie, right? Well, it's real, and it could be a complete game changer for our energy future. So today we're going to crack open this hot box and take a look inside the solid oxide fuel cell, or SOFC for short.
Look, we all know the deal, right? Our world is absolutely hungry for more and more power, but we have to figure out how to generate it without wrecking the planet. It's a massive puzzle, and that's exactly where technologies like SOFCs come in. They offer a powerful, quiet, and really reliable way to tackle this problem head-on.
So, let's meet the star of the show. The SOFC isn't your average fuel cell. It's got some pretty unique traits. First off, its efficiency is just off the charts. It's also amazingly flexible with what fuel you can feed it. But the real kicker, the thing that makes it all work, it runs hot. I mean, scorching hot. And that heat, well, that's where the magic really happens.
To really get how this thing works, we've got to look under the hood. The heart of an SOFC isn't some noisy, complex engine. Nope, it's actually a pretty elegant solid-state sandwich made of 3 key ceramic layers. So let's break down what's actually inside. First up, you've got the cathode. You can think of this as the air intake for our ceramic engine. Its one and only job is to grab oxygen right out of the air. Now, it's made from a really complex ceramic, strontium-doped lanthanum manganite, which, yeah, is a total mouthful. I know, but the key thing to remember is that this material is just perfect for handling insane heat while grabbing that oxygen.
On the flip side of our sandwich, we have the anode. This is the fuel side. This is where you introduce your fuel, whether it's pure hydrogen or something more everyday like natural gas. The anode is usually a mix of nickel and another special ceramic called YSZ, and its job is to act as a catalyst to kick off the chemical reaction that releases all that useful energy.
And sitting right in the middle, we have the most important piece of the puzzle, the electrolyte. It's this solid, non-porous slice of ceramic, and its whole job is to be a very, very strict gatekeeper. Think of it like a bouncer at a super exclusive club. It completely blocks the fuel and air from ever mixing, but it lets one very specific guest pass right through: charged oxygen ions. So how does this whole thing actually generate power? Well, it's like a continuous, elegant dance. Here's how it goes. Over at the cathode, oxygen molecules from the air get split apart, and they grab some electrons, which makes them negatively charged oxygen ions. Then, because of the chemistry, they're pulled straight through that selective electrolyte. Once they reach the anode, they react with the fuel. This creates water, a ton of heat, and here's the most important part: it releases those electrons they picked up earlier. Now those electrons have to take the long way around, traveling through an external circuit to get back to the other side. And that powerful flow of electrons, that is electricity.
All right, so we have to talk about the most defining feature of an SOFC, that incredible heat. See, for that ceramic electrolyte to do its thing and let those oxygen ions cruise on through, it has to be crazy hot. And this is both the SOFC's greatest superpower and its biggest engineering headache.
I mean, we're talking about operating temperatures between 600 and 1,000 degrees Celsius. To put that in perspective, your home oven on its self-clean cycle might hit 500 degrees C. And SOFC is just getting warmed up at that point. It operates at temperatures hot enough to melt aluminum. This is seriously, seriously hot.
And this is the classic double-edged sword, right? On the one hand, this extreme heat is what gives you that amazing efficiency. It's what lets the cell use common fuels like natural gas directly. Plus, the waste heat is so high quality you can capture it to make steam and generate even more electricity. But on the other hand, that same heat puts a ton of stress on all the materials, which means you need expensive, specialized alloys and ceramics that can take that punishment for years without falling apart.
So, how on earth do you actually build one of these things to last if it has to handle those blistering temperatures? Well, engineers have come up with 2 main designs to solve that problem, each with a different approach: the tubular design and the planar design. Let's see how they stack up.
The tubular design, which was really pioneered by companies like Siemens, Westinghouse, is kind of the old-school veteran. It uses these long, really tough tubes that are fantastic at handling thermal stress and have a proven track record for reliability in huge systems. The planar design, on the other hand, is more like a stack of pancakes, just thin, flat plates layered on top of each other. This approach is all about getting incredibly high power density and, hopefully, lower manufacturing costs. So it's a classic battle: proven rugged reliability versus next-gen performance and cost.
And make no mistake, this isn't just a science experiment anymore.
SOFC technology is here, and it's being deployed right now, mostly for stationary power generation, where its quiet operation and amazing efficiency can really shine.
And we're not talking about powering a couple of light bulbs here. A single large SOFC power plant can generate 250 kilowatts. To give you some context, that's enough clean, continuous power for a data center, a wing of a hospital, or even dozens of homes. It just shows you how scalable this tech really is. So what's next? Well, the holy grail for SOFC research right now is to bring that operating temperature down. If engineers can cook up new materials that let these cells run efficiently in that 600 to 800 degree range, it opens up a whole new world. You could start using cheaper, more common materials like high-performance stainless steel. That would slash costs, boost durability, and open the door for all sorts of new applications, maybe even powering big ships or trucks someday. Which leaves us with a final, pretty fascinating question. The performance is there, the efficiency is absolutely world-class, and the fuel flexibility is a huge plus. The main hurdle has always been managing that heat and the cost of the materials that can take it. So as our materials science gets better and better, could these solid-state ceramic engines become the quiet, clean, and super reliable heart of our future power grid? It's definitely a very hot topic.